you a force event. Force event can come new observation. That's why you have to be so critical about everything you do until you can trust what you're doing. So you can see here on the right, for example, global muon misidentification probability. So you can see that as the kaon momentum is increasing, the misidentification actually here increased. And for the pion as well, is that also misidentified?
You can click the little arrow.
Can I?
Yeah, there's a, oh, not that one. Okay.
Oh, I see.
The one above, on the right.
On the right? Anyway, that's okay. I should bring this next time. Yeah, it's misidentification. So basically we're looking here and we're checking our understanding on misidentification of muon with a kaon or with a phi. And let's move on to the start of the design of the CMS. So actually we said a lot, so we don't have to repeat all this. We talked about magnetic field, electromagnetic, etc. Okay, tracking requirement. So when we build a silicon detector, what are the requirements for the silicon detector? So momentum resolution goal was that it will be 0.1 time the PT. Why am I talking all the time about PT in LHC? Why always transverse and not radial or the Z? Why when you have an experiment like LHC, you always talk about transverse missing energy, transverse momentum, transverse this, transverse that? Any guess? Yeah, and what?
Is that the direction that the particles are going in after the collision? The transverse direction?
Also, but like, I mean, they go like that, they hit, and then they splash all over the detector. But why the transverse is the important, very important one? Okay. Think about relativistic effects. Well, what relativistic effects are like kind of like?
So it has to do with the contraction.
Right. So basically, there's few things going on here. In the Z direction, it's not like I have an E plus E minus collider here. I have a PP collision. Now the proton is not a fundamental particle. It has quarks and gluons. It's mostly gluons, and like a big fraction of this proton and these energies are basically gluon. And when you have collisions, you don't know the momentum. You don't know your center of mass energy in the Z direction. So you don't know the boost, basically. But there's no boost in the transverse direction because they are not boosted in this way. They're only boosted this way. So we like the quantities that are orthogonal to the boost, which are not affected by this relativistic effect. Right. So this is very important. So that's why we talk about PT resolution. So the transverse momentum resolution. And why do I care about high momentum? Like I told you, the higher the momentum, the more straight the particle go, and then the resolution is a big effect here. So one of the golden channel in LHC is the one I showed you in one of the first slides here, and it's the Higgs going to 4 muon. And it goes to ZZ, and each one of the Z goes to 2 muon, and you get 4 beautiful tracks in the detector. So, but these tracks will be at high momentum. So that's why you can build a detector and have the golden channel poorly measured. That will be a joke. So they knew from the beginning, I need to be able to measure the lepton charge up to 2 TeV. And the lepton charge means I need the bending of, I need to figure out how much this muon was bending. That's what it means to measure the charge. And I need to know if he bended to the right or the left. And I need to make sure he goes to different electronics. So I have so, and I have to match the calorimeter resolution, and you always have to match energy to momentum. So, and I need pattern recognition, because large PT leptons, like muons and electrons, I need to be able to have, have basically pattern recognition to identify these tracks. So there was pattern recognition for each one of them. And I have to add the vertex information. So really, when you construct a track, you get the information from every piece of the detector about this guy and try to combine it and have a probability likelihood to figure out, is it actually likely that this is a muon or something else? So this is the silicon tracker. The purpose was again to measure momentum and charge of charged particles. And the method was to use many concentric layers of thin, finely segmented sensors made of silicon. Silicon, again, what's the idea behind silicon? Silicon is you take some solid state, basically detector. You take the silicon, and some of it is doped with P, and some is, right? You guys know about doping a little bit. Some are P and some are N, right? Whole and charged particles, right? So some, and then what you do is like building a diode, right? It's like building a diode. So there's hold and charged particles, and what you do is you use a reverse potential at the layer that the two are touching each other. So when a charged particle will go through, it will create a charged particle and a hole, and they will go to the reverse direction. So basically they will close a circuit. Once they close a circuit, you get a signal in your electronic. A particle went through here. So that's why you use like silicon tracker. So a charged particle transversing sensor will produce a heat. You join the heat to make a track, and from which you can measure the momentum. So a trivia here, 70 million individual detector segments were part of this detector, 70 million. So not only it's hard to build, every piece of it, you can imagine how much work students had to do. It's like every one of the 70 million had to be tested, right? We can't put in one. Every one of them, we have to know how good it is. We can't have one that's like, I don't feel like measuring this one, it's probably like the other one. No, everyone is tested, everyone is documented. You have a record on every little thing. Now the segments are about as thin as a human hair. So this is how much you have, 70 millions of them. Quite impressive. So two silicon sensors bounded together here. There's a picture, and that's a silicon trip. And you can see here more than 1,000 tracks per event, and basically extreme segmentation. And the ones that are problematic are the ones that are doing the full circle inside the silicon. And you can see here the CMS silicon tracker. Like I told you, there is like the 3-1 here close to the beam pipe, then you have another 10 here, and 9 here, and like 3 and 9, and there's like all this like different layers of silicon everywhere. And this is where, and from every one of them, you can imagine the cables coming out. So how do we use these 70 millions and all the cables, and everything has to be well connected? It's an impressive work. Then comes the electromagnetic calorimeter, where the idea was to measure the energy of electron, positron, and photon. And the method was to use 80,000 crystals of lead tungsten, and they absorb the particle and produce light. And the amount of light produced is proportional to the energy of the particle. And you have photomultiplier that capture this energy and send it to the electronic. We have a signal. So it's all like engineering here that everyone has to do. Now, interesting fact is that each crystal is 98% metal, but is completely transparent. I still don't know why I have to like I never had the chance to actually look into it. But this is really crazy. It's totally metal and it's totally transparent. I think a lot of this crystal came from Ukraine, if I'm not mistaken.
It's not metal,
It's glass. But yeah, it's actually, you need excellent energy resolution, because one of the discovery channel in the RC was the Higgs to gamma gamma, and you have to make sure that each one of these photons is well absorbed in one crystal, and all the shower as much as possible is in it, so that you're able to measure as much possible the energy. And the higher the energy, obviously the better the resolution. This is like, again, every crystal had to be measured, and 75,000 lead tungsten crystal. Look how beautiful they are. It's like diamonds. And you have to understand the showering, and you have to understand the energy collection and how much you're losing and why is the noise. So you have noise from electronic and noise from pileup and everything. And it has to, after you understand all that, you have to learn how to calibrate it. So how do you do calibration? Any idea? So imagine, like, what would you do to calibrate these things? Like, I need to know that when I find an electron, I actually find an electron. So what would I do?
You do collision that you know that collision.
That's right. You actually either throw pion into the detector or do something, make a test beam full of pion and hit this piece of detector and calibrate, because then you will discover that when I generate 100 GeV muon or pion, I actually collect 20 GeV. So it's very important that you know to calibrate. 100 means 20. This angle means this angle. There's like really a lot of work. The next one after electromagnetic calorimeter came the HCal, which is the hadronic calorimeter, and there the purpose is to measure the hadron and their energy of the proton, neutron, pion. The method was to particle deposit energy in the layer of the brass. They lose energy there, and then this energy is measured by interleaved layers of light producing plastic tiles, scintillators. So you have, it's like a sandwich. You lose energy in the brass, and then that produce like particle that propagate to the scintillator, create like light, and then the light turns into electrons, and then like we collect the signals. Okay, so we have the we have the concentric layer of the hadronic calorimeter, and then comes the magnet. Okay, so all that is inside the magnet to give a curvature. And here is the magnet. The basic goal is to measure 1 TeV muon with 10% resolution at 4 Tesla. And you can see from the magnetic field and how you calculate the magnetic field, you need like 21,000 turns per meter, 4 layers of them. And the challenge is 4 layer winding to carry enough current, and the design has to be reinforced so that it's not too heavy and it's good enough. So you could melt 18 tons of gold. This is how much energy is stored in this in this magnet. This is the completion of the magnet. You can see some people inside inside the detector here. And almost the end, we have almost done here. We have, like we said, the data acquisition and computing, also very challenging. Basically, the first we said we're using, what pieces of the detector actually will be used for the trigger? That's actually an important question. Well, I mean, we have the tracker, the electromagnetic calorimeter, the hadronic calorimeter, and the muon detector. Which pieces of this detector will be used for example, for level 1 trigger? What do you guys think? What?
The first layer, the first tracker.
Why?
Because you're trying to figure out how many initial hits that you have.
Okay, but so the issue with that actually is that we don't use the tracker in the trigger. Tracker has so many hits, and it will take forever to save this information, and no, especially if you need to kind of reject events based on it, you can't. It's just too much. You need something that will be quick, that will give me like a segmented information that's fast to use and reject events. So the tracker is a dream. That's actually was my idea to use the. Well, everybody has this idea. Nobody is like, but I had a way to do it. So I showed them a way to do it. So that was different. There is the tracker is basically problematic with the computing power we had back then. So what you use is the calorimeter, both of them, because they are big and segmented relative to the pixel, and you don't need to use every one of them. You cluster them into, like, let's say 3 by 3, and you call this a unit for the detector, for the trigger, and you get quick information. What's the hit over there? You don't need to know that there's one track. You just need to know that there is information that like is not like looking like a big background, like it's only in the forward direction, and you need to know that, like, let's say, like, what will it be a good signal? If you have 2 tracks coming here and they hit only the forward, so it's either forward physics or it's, or let's say you see beams only in one direction. So you know it's background. So events that didn't have timing, so that they came, the track reconstruct in a way, in such a way that they come at the same time from the beam, you can calculate where they came from. So there is timing constraint and stuff like that, and the track should be propagated on the 4 pi, then you know it's not a good event. So we throw a lot of stuff that we are not interested in, and we look at the total energy of this event. If the total energy is very small, that's not an interesting physics, for example. So that's how you use like the calorimetry for the trigger, and the amount of data transfer data acquisition system is about the same as that handled by the all world telecom network today, and that was a few years ago.